You know, we throw around words like work, energy, and power every day. But what do they really mean in the world of physics? Well, it turns out they had these super precise definitions that connect absolutely everything, from a simple falling apple to the engine roaring in your car. So today we're going to demystify these core ideas and see how they're all beautifully tangled together.
So let's kick things off with a little puzzle. Just picture yourself pushing against a solid brick wall with every ounce of your strength. You're sweating, your muscles are screaming. It definitely feels like hard work. But what if I told you that, according to a physicist, you've done exactly zero work on that wall? I know, it sounds completely wrong, doesn't it? Let's figure out why.
Okay, here's our game plan. First, we're going to nail down what work actually means in science. Then, we'll dive into energy, the fuel that makes work happen, and see how those two are connected. After that, we'll talk about why energy is never really lost, just changed. Then we'll define power, which is all about how fast work gets done. And finally, we'll watch all these ideas collide, literally.
All right, first up, defining work. And right off the bat, you've got to kind of forget the everyday meaning. In physics, work has nothing to do with how tired you feel. It has everything to do with actually making something move. And the definition is actually pretty strict, but simple. For work to be done, two things have to happen. One, you apply a force, and two, the object has to move. No movement, no work. It's really that simple. And that's the answer to our little wall puzzle. The wall didn't budge, so no matter how much you pushed, no work was done on it.
Now, of course, there's a formula for this. Work equals force times displacement. But see that last little bit, that cos theta? That theta stands for the angle between the force you're applying and the direction the object is actually moving. And trust me, that little angle is a huge deal.
And that angle gives us three key scenarios. First, you've got positive work. You push a box and it moves forward. Easy. The force and motion are perfectly aligned. Then there's zero work. Picture carrying a heavy grocery bag. You're lifting up with the force, but you're walking forward. That's a 90-degree angle between force and motion, so technically no work is being done on the back. And finally, negative work. Think about the brakes on a car. The car is moving forward, but the braking force pushes backward, actively working against the motion.
Okay, so if work is the act of making something move, what do you need to actually do that work? Well, that brings us to our next big concept, energy. The best way to think about it is like currency. It's the money you have to spend to get any work done. It's the go that makes things, well, go.
And the official definition, it's actually beautifully simple. Energy is just the capacity to do work. If something has energy, it has the potential to make something else move. It's like this stored-up ability to cause change in the world.
Now, in mechanics, we mostly talk about two main flavors of energy. On one hand, you've got kinetic energy. This is the energy of pure motion, like a car speeding down the highway. And on the other hand, you have potential energy. This is stored energy. Think about the water held back by a giant dam. It's not moving yet, but because of its high position, it holds an incredible amount of potential to do work if you let it go. Okay, so we've got work, which causes motion, and we've got energy, which is the capacity for motion. So how do they link up? Well, here's the big idea. Work is just the act of transferring energy from one place or one object to another. It's the transaction.
And of course, there's a formal name for this relationship. It's called the work-energy theorem. And all it says is that the amount of work you do on an object is exactly equal to the change in that object's kinetic energy. They are directly and perfectly linked.
And the math here just makes it crystal clear. The work you do is simply the object's final kinetic energy minus its initial kinetic energy. So when you push a stalled car to get it moving, you're doing positive work and its kinetic energy goes up. When you hit the brakes, you're doing negative work and its kinetic energy goes down. It's a direct energy exchange.
All right, this next part, this leads us to one of the biggest, most profound, most fundamental rules in all of science. Seriously, this one governs everything in the cosmos, and once you really get it, you'll see the world in a whole new way.
It's called the principle of conservation of energy. And it states that energy can neither be created nor be destroyed, but can be changed from one form to another. The total amount of energy in the universe is fixed. All we can ever do is move it around and change what it looks like.
A falling ball is the absolute perfect example of this. So, at the very top, at point A, it's totally still. All of its energy is stored up as potential energy because of its height. Then, as it starts to fall to point B, that potential energy starts converting into kinetic energy. It's basically trading height for speed. By the time it gets all the way to the bottom at point C, right before it hits, all of that potential energy has transformed into kinetic energy.
This chart here shows you exactly what's happening. See that first bar? That's the potential energy, and as the object falls, that bar gets shorter. Now look at the second bar. That's kinetic energy. It starts at 0 and gets taller as the object speeds up. But here's the magic. Look at that third bar, total energy. Its height never changes. The energy is just shifting from the potential column over to the kinetic column, but the total amount stays perfectly, absolutely constant.
So we've nailed down work and energy, but there's one last piece of this puzzle we need to talk about: power. And power is all about adding one crucial ingredient to the mix: time. It's not just about how much work you do, but how fast you get it done.
Power is simply the work you do divided by the time it took you to do it. Imagine two people have to lift the exact same heavy box onto a shelf. They both do the same amount of work, right? But if one person does it in 2 seconds and the other person takes 10 seconds, well, that first person is 5 times more powerful.
We talk about power constantly, especially with things like cars and engines. The official scientific unit is the watt, but we're all way more familiar with horsepower. So what does 1 horsepower actually mean? Well, it's just a handy way of saying 746 watts of power.
And here's where this whole thing hits you right in the wallet. Your electricity bill comes in kilowatt hours. Now, a kilowatt is a unit of power. An hour is a unit of time. And if you remember from the last slide, power multiplied by time equals energy. You don't get billed for how fast you use electricity, you get billed for the total amount of energy you consume.
All right, for our last section, let's put all these ideas, work, energy, conservation, together and watch them play out in a really dynamic way. Collisions. This is where you can see the laws of energy in dramatic action. We can basically split collisions into 2 main types. On one side, you have an elastic collision. Think of billiard balls clicking together. In a near-perfect bounce like that, the total kinetic energy of the balls before and after the collision is pretty much the same. But then, you have an inelastic collision, like a car crash. In this case, the total kinetic energy after the impact is a lot less than it was before.
And that leads us to one last, really important question. If we just said that energy can't be destroyed, but we know kinetic energy is lost in a car crash, where did it go? Well, it didn't just vanish into thin air, it was transformed into the loud crunching sound of the impact, into heat from all that bending metal, and into the work it took to completely deform the cars. The energy is all still there, accounted for. It's just changed its disguise into forms that are a lot less useful. A perfect, if a bit destructive, example of conservation in action.